Hello and welcome to this lecture, the Harmonic Oscillator. In this lecture, let us see and solve set of problems. By doing so, you will be familiar with the harmonic oscillator, and so let us see the first problem here. A block of mass m is connected to a light horizontal spring, that is, spring mass is negligible, and the system is placed on a frictionless surface as you can see here, and the block is displaced from equilibrium position and released from rest. So then it undergoes simple harmonic motion because there is no external force on this. Just initially it is stretched and then it is released. So once it is left to itself, then it undergoes simple harmonic motion. So consider the center of mass position. Basically, so this oscillation happens in only one dimension, in this manner, in one dimension. Hence, the center of mass moves only in one dimension. So basically, we have to consider center of mass um, so if whether it is uniform mass or non-uniform structure or non-uniform mass, the center of mass, if we consider, that will work for every case. So yeah, and equilibrium position, let's consider at the center of mass, even if some other structure is given, like a spherical shape with half side has mass and the other half is empty or something, whatever. But um, once you calculate the center of mass, draw a line, and that you may take as x equal to 0 position, so that the center of mass will move, oscillate only in one dimension. So if this is the center of mass, it just moves like this and like this. So it just oscillate, so that oscillation is in one dimension. So I am taking this x equal to 0 in this way, and this I take as positive x-axis. So, and this x is function of time, and we know that from Hooke's law, when it is stretched. So here it is given that the block is displaced from equilibrium position and released from rest. Um, okay, so it is released from rest. So that means x dot of 0 equal to 0. That is initial initially at time t equal to 0, the velocity will be 0, which is given as x dot. So basically dx by dt is velocity, we represent as x dot. So yeah, now we have this initial condition. Now let's assume that the block is stretched to a certain displacement. So before that, let's write the equation. So the force on the block of mass is given by Hooke's law. I am putting subscript s, which implies the spring force is equal to minus kx. So basically, the force when we stretch the mass towards this side, the force will be opposite towards the negative x-axis. That's why it is minus k, and it is function of t. So as x changes, the uh, force experienced by the block mass due to the spring will change. Now from Newton's second law, we know that mass into acceleration equal to force, and acceleration is m t square x by dt square equal to minus kx x of t. So now we have this differential equation. I am trying to write here itself so that it will be easy. So I am just rewriting the equation in a proper differential form basically. Plus k by m x of t equal to 0. So now for these kind, this is a second order linear differential equation. Also it is um, so now we can solve this differential equation, and when we solve this, so we get imaginary roots for this. So x of t will be in the form a cos omega t plus b sin omega t. Since we have here k by m times x of t, so omega equal to under root k by m. Please find ways to solve the differential equation. So if I start explaining the differential equations, it will take so much time, and we cannot focus on simple harmonic motion and the harmonic oscillator. So it will be difficult for me to deliver the concepts related to the harmonic oscillator if I keep on going with differential equations and so on. So you find other ways, other resources to uh, s- learn about differential equations and solving them. Otherwise, I will also do that, but in the another lecture and not in this lecture, because in this lecture our goal is to get familiar with these concepts. So based on that, when you solve this differential equation, it will be in this form, and omega would be k by m because we have k by m term here, and this is called natural frequency omega. So basically it is the frequency, angular frequency of oscillation. So the block m here, it will move this side and then come back to x equal to 0, and then towards the negative x-axis side and so on. So here a comma b both are constants. So we got two constant. The solution will be in this form. Now to determine these constants, we need two initial conditions. We need two initial conditions because we have two constants. So already we have one initial condition given, that is x dot of equal 0 equal to 0, but we don't have another initial condition because it is not given. So here it is said that the block is displaced from its equilibrium position and released from rest. How much it is displaced is not given, so let's assume, um, generally it will be given, but in this question it's missed that how much it is displaced. Let's assume it is displaced by A from equilibrium. So now based on this we can have another initial condition, that is x of 0 equal to a. At time t equal to 0, the mass is at a, and it is released from rest, so its initial velocity is 0. Now let's substitute x of 0, we will get a. So anyhow we have taken the constant also a. Cos 0 is 1, and we know that b sin 0 equal to 0, so we get um, a equal to a, like whatever the constant that we have taken, that's suppose if we have, if a is given as 3, then here the constant a will be 3, something like that. um, Now we have another initial condition. Okay. So we have another initial condition is x dot of 0 equal to 0. So let's differentiate that. When we differentiate, we have to equate to 0. A cos omega t will be minus a omega sin omega t, plus b sin omega t is b omega sin omega t. Now we have to substitute 0. When we substitute 0, this will become 0. Sorry, this b and this is cos omega t. So cos 0 will be 1. So now here we get b omega equal to 0. So b is 0. So now we got x of t equal to a cos omega, that is under root k by m t. This is the displacement that we got. So we have solved the first one. We got a cos and root k by m t. Suppose if it is displaced initially by 2 centimeters, then a will be 0.02 in SI units. Always be mindful about units. Whether it's if it's given in centimeters, converts into meters. Next, we have to determine the time period and frequency of oscillations. Time period and frequency. So here we got the frequency omega, which is angular frequency. So angular frequency omega equal to under root k by m. Then frequency will be how much? Frequency will be omega by 2 pi, which will be 1 by 2 pi under root k by m. And time period of the oscillation will be 1 by frequency, which is 2 pi. And when we do 1 by f, we get under root m by k. So we have done with the second question here. Now to find the velocity and acceleration of the block as a function of time. So we have the expression for displacement. Then we have to calculate velocity and acceleration. Velocity is x dot of t. When we differentiate, we get um, as it is cos, we get minus. I'm writing in terms of omega, minus a omega cos omega t. So you can substitute omega equal to, where omega equal to under root k by m. So this is what we, and acceleration will be x double dot. So sorry, I have to write here sign. I'm sorry. Sin omega t. Now when we do double differentiation, we get minus a omega square cos omega t. So this is the expression for acceleration. Uh, we have to find the kinetic energy, potential energy, and total energy. So kinetic energy will be of mv square is equal to half into m into we have calculated velocity. So that is minus a omega sin omega t. Then we write a square omega square sin square omega t. And potential energy of the spring is half k x square. So that will be half, um, and we know that omega square is equal to k by m. So k equal to m omega square. So I am substituting for k here m omega square and um, x I have already found that it is a cos omega t. So that will be a square cos square omega t. This is potential energy and kinetic energy. So total energy T is equal to Ke plus Pe. So that will be half m a square omega square. So these terms are common in both. So I am taking common and then adding sin square omega t plus cos square omega t. This will give us half m a square omega square is the total energy, and also we know that k equal to m omega square, so we can write it as half k a square. This is the total energy. So we have got the expression for total energy, which is depending on the amplitude, that is how much stretching we are doing, as well as the spring constant k. So we have done with the fourth. Fifth one is we have to identify the position where the block attains maximum velocity, and we have to find its magnitude. Also, we have to identify the position where the block experiences maximum acceleration and also determine its value. Yeah, so we have expression for velocity and acceleration here. So I'm just wiping out this so that we can work the fifth and sixth question. So yeah, this is velocity. Velocity is equal to minus a omega sin omega t. So when will the velocity will be maximum? When sin omega t equal to 1. That is when omega t equal to pi by 2. X dot of t will be absolute value we have to take. X dot of t absolute value will be a omega. So here sign doesn't matter because sign is just indicating the direction in which the velocity is happening. but whatever is the direction, uh, the magnitude we are uh, having concern here. So that is j omega. Now when omega t equal to pi by 2, what will be the x of t? X of t expression, we know that it is a cos omega t. Now when omega t is pi by 2, x of t will be 0. So velocity is maximum at equilibrium position. Um, when x of t equal to 0, velocity is maximum and its value is dot of t maximum equal to a omega. Similarly, for acceleration, you can see here acceleration. Acceleration is max. Acceleration is maximum when omega t equal to 0. That is x double dot of t equal to minus a omega square cos omega t. Now at omega t equal to 0, uh, the magnitude of acceleration will be a omega square. So we have to substitute omega t equal to 0, x of t. So when x of t equal to a cos 0 is equal to a. So this is where acceleration is maximum. So velocity is maximum at x equal to 0 and acceleration is maximum at the uh, stretch to at the position to the extent where stretching is done, and that is the amplitude. So let's say that this mass will be oscillating from here to here. So the acceleration will be maximum at these points. Acceleration will be maximum at this point and this point, whereas velocity will be maximum at this point, x equal to 0 point, b max, and here a max. Yeah, so this is the first problem that we have solved. Now we have the second question. A simple pendulum consists of a point mass m. It is suspended from a light inextensible string of length L. So the length is fixed when the mass is tied to it, and also it is light, so the string is massless. The pendulum is slightly displaced from its equilibrium position and released. So initially it is the pendulum is in vertical, but we have take holded it and moved in this manner. So then it undergoes simple harmonic motion. Now we have to derive the expression for angular displacement, linear velocity, angular acceleration, and linear acceleration. Expression for kinetic energy during oscillations, and also derive an expression for potential energy of the pendulum. Yeah. So angular displacement, what we have, let's take a reference. What the reference I will take is anti-clockwise direction is positive, That is, when the angle is in this direction, we will consider that as positive. So we have to um, derive an expression for angular displacement. So now, when the bob is moved in this manner, when it is at this position, what will be the forces on this? So we have force due to gravity in the downward direction, like so mg. Now there is an angle theta between the vertical and the orientation of the pendulum. So I'm just extending this line with the orientation of the pendulum. So now this angle also will be theta. Now if you form a right angle triangle, so now as it is mg on this side and this is adjacent side, so the force along this direction will be mg cos theta. Now the force along this which is opposite side will be mg sin theta. So I'm just drawing perpendicular here mg sin theta. Now there is also internal forces because it is connected to a string. There will be tension in the output and also here. So now here you can see that the two forces, tension and mg cos theta, will balance each other. That's why the mass will be in connection with the string while it is oscillating. So that means um, T tension T equal to mg cos theta. So now the only force is mg sin theta and it is along theta cap direction. So in polar coordinates we have r cap and theta cap. So this is along r cap. Along r cap the forces are equal and the perpendicular theta cap is perpendicular to r cap. Okay, and along theta cap, so along theta cap, what is the force? So mg sin theta. Now this will be minus mg sin theta because we have taken it is in this direction, but we have taken anti-clockwise as positive. That means um, when it is going, when it is at this position, the force is experienced in this direction. So that is negative force because it is opposite to the convention that we have taken. So in the clockwise direction, it is minus mg sin theta because theta is negative in the downward direction, in the clockwise direction. Um, yeah. So now let's write Newton's second law. When we write Newton's second law, we get ma is equal to force, that is m. Uh, Displacement is, let's consider displacement as s of t by dt square equal to minus mg sin theta. So hmm, s of t is nothing but the arc. S of t is the um, distance traveled by Bob along the arc. and we know that the arc length will be equal to radius times angle, and radius here is nothing but length L. So length L is L, for example, times theta of t. Now when we substitute this into the equation, we get m t square L theta of t by dt square equal to minus mg sine theta. So that will give us d L. L is a constant, so I am taking outside theta of t by dt square equal to minus g sine theta. So here in the question it is mentioned that simple harmonic motion. So when it is simple harmonic motion, uh, theta will be theta has to be small in this case. Usually theta less than 10 degrees. Not usually, but it has to be less than 10 degrees to satisfy the condition. So when theta is small, sine theta will be approximately equal to 10. This is reasonable approximation as long as theta is less than 10 degrees. So for simple harmonic motion case, that's the thing. So L equal to minus g theta of t. Now we can write the differential equation as g by L. So it's same as differential equation in the previous case of spring connected to block of mass m. So this is theta of t. So now we got with this differential equation, and we know some initial conditions. So for this case, we know the initial conditions that what is theta of 0. We need to know the two initial conditions. Theta of, sorry, theta of 0. This is equal to, it is released at some angle theta. Uh, Maybe it may not feel so when we have used the same variable. Let's consider that theta naught. So it is the bob is moved such that the initial angle, this angle is theta naught. So it is moved till theta naught, and then it is worked on. Also the velocity, initial angular velocity theta dot of 0 equal to 0, because it is taken to certain height and then released from there. So initial velocity will be 0. So when a mass is moved against gravity or thing, initially the velocity will, suppose if a ball is released from the top of a building, the initial velocity will be 0. Then it starts to accelerate at a rate. of g. Similarly here, initial velocity will be uh, 0. So the total energy will present in the form of a potential energy. Now, using these initial conditions, we have to solve this equation. So basically, if you solve, you will get theta of t is equal to a cos under root g by l t plus b sin under root g by l. So this is one form of writing, but most useful form. We can also represent the solution in the form as a cos omega t plus 5. So let's not put here a again because both a's cannot be same. So let's put here as c1. C1 and C2 are two constants, and we get this a cos. So it is useful. It is useful to write the solution in this form. So for angular displacement, let's put this constant as a theta, and this is a phase angle phi. It is called the phase angle. Now we can determine the. So here basically this is a constant, and the phi is also constant. So we have to determine that. Now for theta of 0, what will be the thing? A, just subscript for angular displacement constants. So cos of 0 plus 5. Now, so we got this one condition, that is a theta cos phi is equal to, uh, sorry, it's not um, 0, it's theta naught. So this is the one initial condition. Theta of 0 at time t equal to 0, it's theta naught. When we substitute time t equal to 0, we get a cos phi is equal to theta naught. So this subscript is just to say that we are dealing with the angular displacement and there is no other significance for the subscript. This is one condition. The second condition is that we have to differentiate this theta dot of t. So drag when we do theta dot of t, we get, so as it is cos, we get minus omega sin omega t plus 5, and we have to substitute it, so we get 0 equal to minus sin of omega t is omega times 0 plus 5. So here a theta omega can't be 0, so sin phi has to be 0, so that means phi equal to 0 in this case. So yeah, sin phi, then this will give us theta of t is equal to cos omega t, and uh, yeah, so here a is nothing but A subscript theta naught is equal to A subscript theta naught cos phi. Phi is 0, so cos 0 is 1, which is equal to theta naught. So theta of t will be theta naught cos omega t. This is the final expression that we have to find here. Anyways, writing in this cos omega t plus phi form is so much significant, and it has more meaning uh, as we are dealing with physical systems than writing in this manner. So writing in this in terms of phase angle phi is more meaningful for physical systems. So we have done with the first question. The second question is determine linear velocity. So we got angular displacement. Then we have to calculate the uh, angular velocity. Angular velocity omega is equal to theta dot, which is minus omega theta naught cos omega t. Now linear velocity is equal to r times omega, and we know that r is L times sorry, this is so here angular velocity, let's not put use this omega because it will be a confusion. So what I will do is I will write uh, angular velocity with this sign. So that will be r times omega. So then we will get minus r. We know that it is L omega theta naught cos omega t. This is the linear velocity. Sorry, theta dot, when we differentiate, we get sine omega t here. Now, angular acceleration alpha theta double dot, which is minus omega square theta naught cos omega t. And what is linear acceleration? Linear acceleration will be r times theta double dot r times alpha, which is minus L omega square theta naught cos omega t. Okay, so we have found this linear acceleration also we have found. Next is kinetic energy and potential energy we have to find. Kinetic energy K equal to half mv square. Here v is linear velocity. Half into m into linear velocity is L square omega square theta naught square sine square omega t. This is uh, next we have to find the potential energy. So potential energy we can find with respect to reference. So here we have to take the reference. So let me go to the figure. So we have this thing, or else let me wipe out. Okay, so let me draw and show you how to calculate the potential energy. So this is ceiling, and we have a bob. Now we have displaced it, or it is oscillating. So consider the center of mass. I'm just drawing the center of mass. I'm just I'm just drawing this triangle here for illustration. It's not so straight, but just assume that. So this is where the center of mass points I'm drawing. So it is oscillating from here to here and then again to the this side. So the potential energy at this point is zero. So that's the reference I'm taking because it is not experiencing any force because the tension force is upward and weight is downward, so both cancel and the potential energy here is zero. Now distance between these two, we have to see how much distance this is. So when okay, now when the center of mass is here, the force experienced by that will be F is equal to minus mg sine theta, which is equal to du by dx, minus du by dx. Sorry, minus du by d theta because the potential energy is changing with the angle. Yeah, because sine theta is the variable here. Or we can do like this, or in the best intuitive way is to calculate the distance, how much it is traveled, at what height it is existing now. So to do that, we have to make a triangle here. We know that this angle is theta at some time t is theta, and this is 90, so this has to be 90 minus theta. Now this is 90 minus theta and 90, and so here we will get again theta. Now so we have theta here, and so this length we have to find now. In order to find this, we can find this also. directly. The total length is L, and what is the this particular distance we have to find. That will be equal to cos theta equal to this distance. Suppose let's consider this as x by hypotenuse, and the hypotenuse is the length of the pendulum. So x is equal to L cos theta. So this is L cos theta. And let me write some. So this is x equal to L cos theta. Then this total is L, so L minus L cos theta will be L into 1 minus cos theta. So this much height it is moving. So potential energy is equal to, we know that mgh for a mass. So mass here we have to calculate with reference. So here reference it is 0. So at a height L into 1 minus cos theta height, the P will be is equal to mg h is L into 1 minus cos theta. So this is the potential energy, and we really don't need this. Without this we can calculate. Mm, so now we got potential energy which is mgl 1 minus cos theta, and we know that 1 minus cos theta is equal to 2 sine square theta by 2, but that is not so feasible for us anyway. So yeah, we may just keep it as it is, 1 minus cos theta. This is the potential energy, and kinetic energy is what we got achieved previously. Yeah. So this is basically derive an expression for potential energy during the oscillations of the pendulum during oscillations. So we have seen how it is varying with respect to theta. With so the only variable here is theta, so the potential is varying with the theta. And however, the total energy will be constant. So basically, of sine square omega t. Um, yeah, if we substitute, so here we haven't found the omega, but we can find the omega as in the previous case. Omega is equal to under root g by L. So omega square, we know that omega square is equal to g by L. So when we substitute, Ke will become half m L square g by L theta naught square sine square omega t. Now when we can calculate, cancel L and this L. Okay, yeah. So this is a expression for kinetic energy mgl theta naught square sine square omega t. We have done with the second question here. Now let's look at the third question. A physical pendulum consists of a rigid body of mass m suspended from a pivot. The string or rod, so basically this is a rod, also has a mass, and the distance from the center of mass to the fixed point is L. So here the fixed uh, center of mass is this point, as you can see. So the distance is given from the fixed axis. It is given as L. So whenever we are given a problem with this sort, or and we have to consider the length of from the center of mass only. So initially the first step is to calculate the position of center of mass, and then finding the length L if the center of mass is not given. So here we have to derive an expression for torque acting on the pendulum about pivot. Also determine an expression for the angular acceleration of this. Okay. Yeah. So here also we have the same as previously. The force is in this direction, which is minus mg sine theta, because it's up to us what convention we take. I'm taking anti-clockwise as positive always. So yeah, in that case, mg sine theta will be the force downward. And we know that expression for torque is um, R cross F. And we know that R is length L. The distance from here to the center of mass is L. So L R cap. So where is the origin? Origin will be here. When the origin is here at this, if this point is the origin, then the R cap will be, sorry, L R cap will be the case. And cross product with minus mg sine theta, and the direction of this force is theta cap. So this will give us minus mgl sine theta. R cap cross theta cap is z cap, which is perpendicular to both R cap and theta cap. So basically z cap, it is perpendicular to R cap comma theta cap. This is the expression for torque. So torque tau is equal to I times alpha. So here we know the formula for torque. So I is moment of inertia, and alpha is the angular acceleration. So the expression for angular acceleration alpha will be uh, minus mgl sine theta by I. So we have to calculate moment of inertia, uh, and then divide by it, we will get angular acceleration. So now we have another problem. So we have done with the third problem basically. Now let's go to the fourth problem. A block of mass m equal to zero point 0.2 kg is attached to a spring of constant this and lies on a fixed, frictionless horizontal surface. The block is displaced 5 centimeters. So basically, block is connected to, it is lying on a frictionless surface. So this is assume that it is frictionless surface. Um, okay, so equilibrium position x equal to 0. It is stretched up to 5 centimeters, which is nothing but 0.05 meter, uh, and released. So calculate. So the part of the question is missing here. I'm just writing. Give the expression for displacement. So we know that we have already calculated this in the first problem itself. So I'm just directly writing it as x of t is equal to a cos omega t, but a is here 0.05. That's the displacement, and cos omega t. Sorry, yeah, omega t, and we can calculate omega under root k by m. K is 10 by mass is zero point 0.2. So this will give us 150. So 5 root 0.05 cos 5 root 2 t. This is a expression. I have I directly written the final expression because we have worked on this and we know the how to apply initial conditions and so forth. Now let me go to another question. A mass m is attached to this is fifth question. A mass m is attached to a spring of force constant k and suspended vertically from the ceiling. The natural unstretched length of the spring is L, and when the mass is attached, it causes the spring to stretch due to gravity. The mass is then further stretched by this. So derive the equation for displacement of the mass as a function of time. Mm, so we have a ceiling. So when it is not stretched, the length will be L. So always take up to this. Mm, so this is L. Now, in the second instance, what happens is that it is stretched when the mass is connected, it will be stretched to some. When mass is it will be stretched due to gravity. This stretching happens, and in the third scenario, we are stretching deliberately. So imagine this spring. From here, we are deliberately stretching some more, like as given in the question, point 1. So I'm just drawing the lines here. Some so always have to go from center of mass if it is given uniform or non-uniform. Third line is okay. So this is the scenario. So basically, the answer depends on the reference which we take. In the exam, the reference thing will be given. Somehow, the reference will be indicated. But in this case here, I would like to take this as reference. So this is reference y is equal to 0. So here the center of mass will move only in one dimension. I am taking that as positive y, positive y and negative y. So as it is stretched towards downside, let me take this as positive y-axis. It doesn't matter whether you take this as positive y-axis or negative y-axis. So the answer will be same. Yeah. So this is y equal to 0, and also it is given that the mass is then further stretched by zero point 0.1 L. So this has to be uh, zero point 0.1 L. Okay, this is zero point 0.1 L. Yeah. So now let's write the equation. So the force due to gravity will be towards y-axis, and the force due to spring will be upwards. Now when we write Newton's second law in the positive, assuming taking the convention that acceleration is in this direction, let's say, in that case acceleration is positive, uh, in the because it is in the positive direction only, so that will be is equal to uh, in the positive direction we have gravity, so I'm writing j cap minus the spring force will be upwards, that is towards negative direction, hence it is ky y cap. So the spring force will be upwards. Now from this I can write m square m d square y of t by dt square equal to mg minus ky. So all this is happening in one dimension, that is uh, j cap. Here also we have j cap. So everything in one dimension. So there is no worrying about. Now this will reduce us to the differential equation d square y of t by dt square equal to g minus k by m y. So just rewriting the differential equation. Here k by m we can write as omega square equal to k by m, and g is also constant. Omega is constant, g is also constant, and this is a non-homogeneous differential equation. We have constant on this side. So the solution y of t will have two components, yp and yn. Also find how to solve this. So solution for yp will be of the form simple another constant a, and for yn it will be uh, c1 cos omega t plus c2 sin omega t, and we need initial conditions for this. initial conditions is that y dot of when t equal to 0 is 0 because it is stretched and released from rest. And also we know that y of 0 at time t equal to 0 it is at zero point 0.1 L because it is stretched from y equal to 0 towards zero point 0.1 L. So these are the initial conditions, and for particular integral we have a. We let's substitute a in the differential equation. So in that case, what we get when a is a constant, double derivative it is 0 plus k by m times y is a is equal to g. So from this a is equal to mg by k. We got mg by k. Now let's write the y of t as particular solution a is mg by k plus c1 cos omega t plus c2 sin omega t. Now we have to substitute the initial conditions. First initial condition is y of 0 is equal to zero point 0.1 L, which is equal to mg by k plus c1 cos omega t is c1. So this will give us c1 is equal to zero point 0.1 L minus mg by k. Um, yeah. And how about C2? For that, we have to differentiate the y of t and find y dot of 0 is equal to 0. When we differentiate that, mg by k will be 0 plus c1 cos omega t will be um, minus c1 omega sin omega t plus c2 omega cos omega t. Now we have to substitute t is equal to 0, then this will go to 0 and this will go to 1. However, from this we get c2 equal to 0. So overall we can write y of t which is um, okay. Yeah, let me write neatly here. Okay, let me write here. Y of t is equal to mg by k um, mg by k plus C1 is sorry, zero point 0.1 L, zero point 0.1 L minus mg by k multiplied with cos omega t. You can rearrange this and write it all depends on how we take the reference. So sometimes our reference mostly will be given in the question for solving this to get the solution. So we had derived. Now the next question is seventh question. Is it seventh or what? Okay, we have solved fourth, fifth. And now sixth question. A rigid uniform rod of mass m and length L is hinged at one end and suspended vertically from a fixed pivot. The rod is free to oscillate under the gravity. Determine expression for torque acting on the rod above the pivot due to gravity. Also, angular acceleration when it is displaced by an angle theta from the vertical. Yeah, so here it is basically a rod. This is some setup for having a pivot. So we have a rod of length L. Now when we move this, it will go like this. Uh, the rod is free to a uniform rod. So having the length L, so the variation is only along one direction. The in the other direction it is uniform. So basically we can calculate the center of mass based on symmetry very easily. That is the center of mass will be at the center because it is uniform, and so the center of mass will be at a distance L by 2, and it is free to oscillate under the gravity. So in this we can calculate torque, which is equal to force into distance. So here L by 2 r cap cross minus mg sin theta theta cap. That will give us torque is equal to minus mg L by 2 sin theta z cap along perpendicular to the plane of oscillation. And we can also calculate the moment of inertia for this. Moment of inertia I is equal to 1 by 3 m L square. So angular acceleration will be torque by moment of inertia. That will give us minus 3 by 2 g by L sin theta. So this is the acceleration we got, angular acceleration. Next, let's solve the seventh question. So I'm going to just give the clues for this problem so that you can solve by yourself. So here a mass of 10 kg plate is suspended. So the plate is like this. It is 10 kg and it is suspended by springs in this equal springs. Okay, all the springs are equivalent, equal length, equal spring constant. This is a ceiling, and This is the uniform plate. So for this uniform plate, the center of mass will be here. And when the plate is oscillating in this manner up and down like this, the center of mass will oscillate in one dimension. Oscillates in one dimension. So it's not complicated, rather it's very straightforward thing. The only thing is you should be familiar with that center of mass, and the center of mass oscillates in one dimension, but now it is connected with four springs. So now these four springs are in parallel. So what will be the K total, like um, so the K total that we have to consider is 4 times K, which is 4 into 500, that is 2000 Newton per meter. So in just like in the same as the previous case which I have solved, this one same as this, but the thing is K is 4 times of K because four springs are connected in parallel, and then rest everything is same, mass is same, but the position you have to consider with respect to center of mass. So if you see this, with respect to the ceiling, every point on the plane will be at same distance from the ceiling. This is a easy one. You may solve this and write in answer in the assignment in comment. Next problem is two springs with spring constants K1 and K2 are connected in series. Then determine the effective spring constant of the system. So this one is K total or K effective is equal to 1 by K1 plus 1 by K2. So then you can calculate Kt from this expression. Is the eighth problem. Ninth, okay, so this is CSIR and net question. Three particles of equal mass m are connected by two identical massless strings of constant. So I'm writing the diagram. So the diagram is given, but let me draw. Three particles of equal mass m. So each one is displaced x1, x2, x3. So this one is displaced by x1, and this one by x2, and this one by x3. The potential energy of the system, and we know that potential energy P is equal to half kx square. So here when this is mode x1 and this is mode x2, so total displacement of the spring is x1 minus x2, whether it's x1 greater or x2, x1 is greater or x2 is greater, that doesn't matter. So for this spring one, it is half k x1 minus x2 whole square, and for this displaced by x2 and this by x3, so the total spring displacement will be x2 minus x3. So that is, now when you add these two you will get the answer C. So basically, potential energy of the system is potential energy of this spring and potential energy of this spring when these displacements occur. The spring constant K of the spring of determined experimentally by loading the spring with mass m and recording the time period t for single oscillation. If the experiment is carried out for different masses, then graph that correctly represents the result is. So yeah, and we know we have calculated this thing. We know that omega is equal to under root k by यहाँ पे for this spring also has mass. Also externally we are loading with, so we have to consider m plus m. So basically now the center of mass will shift, but even if the center of mass shift, the oscillation angular frequency will be this. So based on that, t will be 2 pi by omega, which is 2 pi into under root m plus m by k. Now t square will be is equal to 4 pi square into m plus m by k. So actually in the options, so this is also a CSIR problem. In fact, CSIR net physics problem. Uh, but anyway, options are given, but I haven't given in the question because we let's plot it by ourselves. So the options are given with T square versus mass capital M. So this is the loading that is given. So initially when the loading is 0, when m equal to 0, what will be t square will be is equal to 4 pi square m by k. So this is some positive value which comes here. And as m is increasing, will increase like this. So this is the option given in the exam. And we can also determine this value which is 4 pi square m by k. So from this we can determine k is equal to 4 pi square m by t square, or wherever there is y intercept. And this one was 9. Then problem 10. Problem 11. So this is also CSIR. So velocity of a particle moving in one dimension is given like this, where v naught and x naught are positive constants with. So now here initially at x epsilon, then in the, so yeah, initially at x equal to epsilon naught x naught. So the CSIR net physics problems. Every problem I'm dealing is physics for now. Okay. Epsilon naught is small, is uh, is very much less than 1. So I can assume this as when it is very much less than 1, it is close to 0 basically. So in that case, v of x equal to v naught sine pi x by x naught is epsilon naught. So basically it is epsilon naught. Now epsilon naught is very much there, so it is 0. Uh, yeah, it is 0. So v of x equal to 0 at x equal to x naught, because epsilon naught is x by x naught, which is very less than 0. So v of x equal to 0 at x equal to 0. X equal to 0 because epsilon naught is very small, times x naught will be 0. Yeah. Now, and in the long run, means towards the extreme, that is when x x by x naught will be 1. For example, in the long run implies x by x naught equal to 1. V of x will be 0 at x equal to um, x naught. Yeah. So in both cases, it is 0. So if you look at options, executes an oscillatory motion around x equal to 0. This is wrong because the oscillation is happening like this. It is mm, it is happening like this. Here velocity is 0 and here velocity is 0. Let me use another color. So it just basically we have to think that's all. Here velocity is 0, here velocity is 0, and this is a position x equal to 0, and this is x equal to x naught. So the oscillatory motion is not happening around x equal to 0. It is extreme. In fact, the oscillation is happening around x naught by 2. At x equal to x naught by 2, the oscillatory motion is actually happening. The other option tends towards x equal to 0 in the long run. No, in the long run implies this is the long run. So this is option is wrong. This is also wrong. Tends towards x equal to x naught. Yes, in the long run it proceeds and it goes until x equal to x naught, and when x equal to x naught, then it will be sine pi and 0 it stops there, and again it will come back. So this is the correct option. Also, it is not executing oscillatory motion around x equal to x naught, and we have seen that it is actually um, executing oscillatory motion around x equal to x naught by 2. So this is also wrong. So we have 11. Now let's deal with 12th problem. So this is a forced harmonic oscillator. Unlike previous case, we have a force on the system. So let's derive the expression for displacement. So it is a mass is attached to a spring and is subjected to an external force. It is yeah. Yeah. So it is having now. Let me write the Newton's second law. That is m d square x of t by dt square equal to, there is a force in this direction and in another direction, if not cos omega t in this direction, and spring force in the opposite direction. This is positive x, the external force, and this is minus k. Now when we take to the other side, I'm just rewriting the differential equation. This is a differential equation. It has two terms. So, like I said, work on your differential equations, natural and particular solution. So here it is cos. So yp will be in the form of something like I'm taking some lambda times cos omega t. It will be exactly in this form, same omega. Now we can calculate this by substituting. Oh, okay, I'm sorry. It's x of t and what we are dealing with x of t is equal to xp plus xn. So here xp will be in this form and substitute xp in the differential equation here. Uh, Firstly, 2 times differentiation. So that will give me minus lambda omega square cos omega t. When I do twice plus k by m times lambda omega cos omega t. This will be equal to f naught by m cos omega t. On both sides we have cos omega t. So let's remove that. We will get now minus lambda omega square plus k by m lambda is equal to f naught by m. From this find lambda. Lambda times k by m minus omega square is equal to f naught by m. Sorry, here f naught by m. So lambda will be is equal to f naught by m into m by k minus m omega square. Hope this is right. Yeah. So that gives us xp. xp will be f naught by k minus m omega square. I hope. Just check this calculations. I'm too tired now to even. But anyways, we have, conceptually we are going well. Just calculations. Just check once. So now we got the XP and natural solution we have to find. So that for that we have to use the initial condition. Uh, okay. So initial conditions will be given. Otherwise, you can just for this question we can just put the general solution. Okay, XP is this. Let me wipe this and since we have the differential equation of this sort, we will know what is the hmm, so x of t will be equal to f naught by k minus m omega square times cos omega t. So we have seen that xp will be in the form of lambda cos omega t. So we have calculated lambda by substituting xp here and we got lambda is f naught by k minus omega square cos omega t. So this is xp. Lambda is this, then we have to get xp of t. This is xp of t, and we know the xn. So I'm just adding to this. So the xn will be in the form of c1 cos omega t plus c2 sin omega. This omega is different from this omega. Okay, this is the forced response frequency due to forced response, and this is natural frequency. So please see the difference omega n here. This omega is the forced term given. That this omega n is equal to under root k by m. Now in the question, if initial conditions are given, we can solve this. But since initial conditions are not given, let's put this in this manner. Also, I have told you in the earlier, we can write this as we can write the same as a cos omega n. Don't forget this omega n is different from the force response given in this manner. And this is the best way to write. Now let's see the last question. Should be the 13th one. So a pendulum at t time is subjected to an impulse force that imparts an initial velocity u to the mass. Determine the expression for angular displacement. So, hmm, okay, we have a pendulum and it is subjected to an impulse force. So basically, the force, impulse force, is equal given by this function del of t. Okay, yeah. So in this case, what will be the scenario? So initially, it is like this at rest. Okay, impulse function is given at this instant where the force on this is zero. Means when it is at rest, the um, it is subjected to an impulse force at this instant. So the velocity u to the mass. Okay. So now when it is subjected to this impulse force, certainly it goes to some angle theta it will go. And when it goes to an angle theta, there will be natural response anyhow because of that. But because of this del function, it will go to certain thing. And we have seen the equation for force and all. Also, it is given small angle oscillations, so sine theta will be approximately equal to theta. Just I'm giving clue on how to solve this. So here t square um, L d square theta of t by dt square. This is the um, acceleration basically. So mass times acceleration is force. Okay, the force has two terms now. One is minus mg sine theta, and we have seen that minus mg sine theta. Sine theta is approximately theta. Also, we have an impulse force delta of t. So when we rewrite this differential equation, it will be we take this and divide with g by l theta of t equal to del of t. Now, in order to solve this, we have to apply Laplace transform. So always learn the Laplace transform and partial fractions. So that will make things easier. So it is essential to learn Laplace transform, and Laplace transform of this will be is equal to s square y of s minus s. This is initial conditions y of 0. Laplace transform is something that is a conversion from time domain to frequency domain, and then we can do the inverse. Okay, that's it. This one. And L of sorry, it's not y, it is theta. I'm just let me write from time domain to frequency domain. So that's why it will be theta of s minus s theta of 0 theta dash of 0. These both are time domain basically. This is and L of theta of t will be theta of s, and Laplace transform of del function, because it is del function, dealing in Laplace is easier. So now we got the equation of this sort. So I'm just putting in the above equation as much space as we want. So theta s I'm taking common, and s square plus what is there here, square plus 1. Yeah, exactly, plus 1. Then we have minus s theta of 0 minus theta dash of 0 equal to 1. Theta s is equal to, let's take all this to this side. So that will be 1 plus s theta of 0 minus theta dash of 0. Then divide this s square plus 1. No, it's not that. But it is here. It is g by l. I forgot to write. Apologies for that. And let me rewrite. So I'm just substituting in the above equation here. So that would be d s square theta of s minus s theta of 0 minus theta dash of 0 equal to, sorry, not equal, plus plus g by l theta of s equal to 1. So now here, so I'll take this as a foundation and practice more problems so to get better at these things. So theta of s I am taking common and s square plus g by l. I am taking other terms to other side. 1 plus s theta of 0 plus theta dash of 0. Now theta of s equal to 1 by s square plus g by l plus s theta dash of 0 by s square plus g by l plus theta dash of 0 by s square plus g by l. So we have to calculate theta of 0 and theta dash of 0 from the question, that is initial conditions. So initially we have given the initial velocity is u. So initial velocity is u. Let me use another color. We have to get the um, initial conditions from the question. We have to derive sometimes. So he initial velocity u is nothing but linear velocity. Let me see how much length is of this pendulum is L, right? So L times theta dash of 0 equal to U. So theta dash of 0 will be U by L. So this is one initial condition. And the other condition theta of 0 is 0. Means initially the pendulum is, it's vertical totally and not making. Hence this will go to 0. So things are getting easier for us. Even if some other angle is given, also fine. Then you have to solve this. You just have to know how to do the inverse Laplace transform. So now I have to do the inverse transform to get thing right. So it will be theta of t will be is equal to, what I will do is I will multiply a square, no? So I will divide and multiply with 1 by g. So here omega equal to omega n, basically natural, is equal to g by l. So what I will do is I will divide by n, and here dividing by omega n and also multiplying by omega n, so that will give me sine omega n t. This um, Laplace transform is this. Now plus theta dash of 0, as you know, it is u by L. Also in this case also I have to multiply with omega n here and divide by omega n here. So sin omega n. Sin omega n t I can take common. Uh, this will be 1 by omega n is nothing but under root L by G plus u by L into under root u by L into yeah, whatever it is, just calculate. In fact, I can take omega n is also common, but whatever it is, you can simplify that. So this is a theta of t that we got. So this is just the foundation for the harmonic oscillator, and the harmonic oscillator is something very important in physics. So basically, it has a lot of implications which are which may not be obvious to you, but these have tremendous implications in physics. And this is just the foundation that I gave in maths and physics. In the next lecture of the harmonic oscillator, we will see more advanced problems, and also the forced harmonic oscillator and damped harmonic oscillator. But I really hope that this will be a good foundation for the next lecture. So in the next lecture, we'll conclude with all the problems. And if you have any questions regarding this, please write in the comments. Thank you so much for watching.